So my name is indeed Lieke Gelderloos, as this just said. I am indeed a PhD student in Tilburg University. I'm also teaching some NLP courses in Vrije Universiteit Amsterdam. And the work that I'm talking about today is very much on the cognitive side of the things that I'm interested in. So this is really sort of the core of my my thesis work, but I'm also actually interested in a work that falls a little bit more directly under the NLP umbrella, which is about grounding of language in vision, and also specifically regarding sort of weakly supervised models that ground language into vision, but also speech into vision directly without having annotations in between. So this is sort of a different line of my work. That's something that my research group works on, but it's not, so that's something I collaborate on sometimes. So I have a somewhat stronger links to NLP than this talk might suggest. With that being said, I hope that this talk is very interesting to NLP interested people as well. Some of the methods will look very familiar. Maybe the research question does not, but yeah, let's go into it. So this work was presented at CogSci last year, which is the cognitive science, big cognitive science conference. And it's something I worked on with Alireza Mahmoudi Kamalabat, who was a master's student at the time and is currently working on his PhD at KTH in Stockholm on robot-assisted language learning. And Afra Ali Shahi, she's my main supervisor, and she is an expert in computational models of language learning. So also very much in the middle of cognitive science and computational linguistics. Okay, so I wanted to open with this tweet by Jan Le Cun. Oh wait, I cannot navigate the slides using, yeah, there we go. So this was like a month ago. This was posted on Twitter. This tweet saying long-term progress in AI will come from programs that just watch videos all day and learn like a baby. I don't know what your initial response to this is, but on Twitter, a lot of people, specifically like psychologists and people who know about language acquisition in humans, were very sort of skeptical about this. So they were kind of like joking, saying things like, as anyone who has spent even a minute or two with babies knows, they learn exclusively by putting random objects in their mouths, which it's kind of true, right? It's not exclusively that way, right? But this is definitely a major part of exploring the world as an infant. Of course, this is kind of like in jest, right? This tweet by Jan Le Cun was also taken out of context. Actually, this piece itself was about a self-supervised vision model that was released recently, and it's very much it's actually very much going in this direction, that we want models that learn independently without having a lot of supervised and annotated data, which is actually very much what the work that I'm presenting today is also in spirit related to. But I think the point that Jacob Eisenstein is kind of like making here is not just about like having access through data by putting objects in your mouth, but it's also about the child is putting the object in their mouth, right? So this child is doing something actively. It's actively exploring the world. It's just not just sitting there watching videos, but it's actually actively engaging in the world. And the idea here is that is actually a very important part of learning. And this is sort of the main idea that in the work that I will present next is kind of like the founding. Yeah, like this is the thing that we want to explore. What changes about learning if we assume that the learner is an active participant? That's sort of the basic thing. Okay, so what is it that we actually worked on? So we work on a task called cross-situational word learning. Well, actually, the task is word learning or referential learning. So learning which word refers to which object. And this is a process that is very often modeled computationally in cognitive science. And basically, there are different ways to implement this. So there are sort of rule-based algorithms. Well, not really rule-based, but like, yeah, just step by step. And then there are more statistical methods, but all of them are based on this premise that if you are able to track over multiple co-occurrence which objects and words appear together, eventually you will figure out which word labels which object, right? That's the basic idea. Now, as I said, there are different ways to model this, but what these models have in common is that typically the learner is modeled as a passive observer of language and objects in the world, right? So this is the Jan LeCun saying that, okay, babies just watch videos all day, right? And I don't think that that's actually the case. And we know that this is not actually the case. So we know that children are actually very curious explorers of the world. We know this from developmental research. So Celeste Kidd is someone who is studying curiosity in development in children learning about the world. And she has shown that this Goldilocks effect in visual category learning, I think this was, but she has several studies on the topic by now. And this is, she has shown this Goldilocks effect, which is like children are particularly selective with their attention towards objects that are of intermediate predictability. So they are not as interested in objects that are super familiar to them already and that they know exactly what's gonna happen. And they are also not as interested in things that are super unfamiliar and completely unknown to them. It's the things that fall in between that draw their attention. So this is, and the idea is that, okay, this is a phenomenon that shows curiosity, right? And that might help, that might be beneficial to learning in some ways. The second study that I'm pointing towards here from this is actually computational cognitive science. This was a study in visual category learning that showed that selecting input according to a definition of curiosity that takes these things into account, so both unfamiliarity and somewhat familiar, right? If you take both these things into account, that can actually help learning. So this was studied by Katie Toomey and Westerman, and I will come back to this later because we actually based our definition of curiosity on this particular paper. Okay, so in this study, the goal is to see whether if we select input curiously, we can change things about the cross-situational learning path, let's say. And if we do that, then how should we define curiosity? What is the way to define items that are beneficial to learning, right? So let me see what slide I have next. Right. And we do this using a model that is able to learn to map objects to words and also words to objects. And so this is a two-part task, let's say. So the way that we frame this task is a two-part task in which you have a production module and a comprehension module. And the comprehension module sees a bunch of objects, receives a word, and points out which object is they think is the correct referent in this case. And the production module receives one object and finds the word in its vocabulary that it thinks is applicable. That's the characterization of the task itself. Now the thing about this model, and I will go into its workings in detail a little bit further, but the thing about this sort of characterizing thing about this that makes self-supervision possible and that also makes curious input selection possible is the fact that although we have two separate modules, they can actually feed into each other. So the production module's output can be used as input to the comprehension module and the other way around. Okay, so I think a quick look at the data might be in order. So the data, and this is actually, since Liz told me that in these talks you also sometimes try to focus a little bit on like, okay, what are the things that you encountered in your process that maybe were a little bit more challenging than you thought, or were you had to overcome to do your research. And I think the data was definitely one of those things for us. This is actually something that we dealt with in an earlier study already that we published at COXSAI in 2019, in which, okay, so we wanted data that had realistic images, but also had single labels for objects that were of a word level, let's say. So we don't want a very broad category label like person for all types of person, or fruit for all types of fruit. We really want names. So we really want boy, we really want orange, right? That's sort of more the level that we are more interested in. And we couldn't really find it. So in the end, what we used, I'm thinking there are several alternatives now, but I still think that this was a good way to solve it. We used the Flickr 30K entities dataset, which is, so Flickr 30K is images from Flickr that have 5 captions each. And then the entities extension of this basically has bounding boxes associated to parts of the sentence. So they highlight a specific referring expression in these sentences and point out which bounding box refers to that. So this was actually like sort of suitable to our purposes. The only thing was that these referring expressions were still multi-word expressions, and we really wanted single words, just because from a modeling perspective, this was much easier. We would ideally want to get to multi-word references, but that's sort of, yeah, that's one of the things that I'm working on currently. So we just wrote a bunch of heuristics to basically select, kick out stop words, select content words like the noun, select the noun that is like most since we have 5 different captions, usually the same bounding boxes refer to in multiple of these, and so we can select a word that occurs more often, and this is how we sort of created this data. And then we checked that the frequencies of our words follow a Zipf distribution, and this is more or less the case. But yeah, so there are several choices that we just had to make here that are all simplifying the problem in a way, right? We're dealing with single words. We also decided, for example, that, so I think in this particular image, we had a word pots, which was associated to multiple bounding boxes. We decided to kick this out, which is not just a simplification for technical purposes, but it actually shows a weakness of our approach from a cognitive perspective, right? It means that our model is not able to deal with these cases when these are real things that happen in the world. So I just wanted to sort of give you a little bit more of insight in the considerations that go into this and the limitations that we're imposing here because of the way that we designed the task and because of the way that the data looks. Okay, so let's look at self-supervised learning. How does this work? In our case, right? So self-supervised learning is one of these terms that right now is getting a lot of traction in both in NLP and in vision and all kinds of parts of machine learning. So let me just say what I mean by it here, right? So this is very specific to our architecture and our task. So as I said, we have this comprehension module and a production module, right? So the comprehension module receives a set of objects. Here they are a bunch of icons. In reality, they are the type of bounding boxes that I showed in the last slide. So in this case, there's a set of 3 objects, a duck, the sun, and the tent. And then it receives a label duck. And then the comprehension module, considers each of these objects in the scene one by one. I will show you exactly how this happens a little bit later on. And then it outputs the object that it thinks is most likely to be the reference. Okay, so what happens next is, this is the trick of having the 2 modules that can feed into each other. So now the output of the comprehension module is used as input to the production module, which outputs a label again. And now we have 2 labels, right? Because we started with the label duck, which we received from the environment. And in the end, we have our own label, sun, which the production module outputted. And we can just calculate the mismatch between these two, right? We can just say, okay, how wrong are we? And can we adjust our representations in order to be a bit less wrong next time, right? So that's sort of the basic idea. I will go into the technicalities. I think already. Yeah, I will go into the technicalities now. Right. So how does this work sort of at the implementation level? So in reality, what we do is we have VGG vectors for these objects. So we just take them from a pre-trained VGG model, which is pre-trained to do object detection in images. And we take like the second to last layer in this, which is kind of standard practice for many NLP grounding language in vision kind of tasks. Many models do it this way. So we do that for every object in the scene, and we process each object separately, let's say. So we have this first object, and we pair it to the embedding of the word that is the input word at this time, right? We're doing comprehension here. These embeddings are start random, right? They're not pre-trained in any way. They start random because that's the task that we're trying to do. We just concatenate the two, and we just have an MLP that outputs some number that we can then feed to a softmax. If we do this for every object in the scene, we can feed these output numbers to a softmax function and get some distribution over which object is most likely to be the referent. Then what we do, I just said that we feed the most likely object to the production module. That is not precisely what we do technically. So what we do technically is we basically use the output of the softmax as attention over all of the objects in the scene. So we have sort of a weighted sum of the 3 objects in the scene, or 4 or 2, depending on how many objects there are. And this is what we use as input to the production module. And the production module then outputs a distribution over the vocabulary, right, with one layer in between. So why do we do that? Well, also because this makes the training possible, right? This makes it possible to backpropagate all the way through the production module and then the comprehension module, because we're using this as attention rather than making a hard choice. If we were doing that, we would need to do some task to because then you have some discretized step, right? Okay. And this was, right, this is important to mention, this was very much inspired by a paper by Roybach et al., who kind of were trying to do this referring expression resolution in an unsupervised way, but really from a computer vision perspective. And in their case, it kind of like didn't really work by itself, also because the objects that they took were not the nice human annotated gold standard. They were just like 100 proposals by computer vision model first. But it did add a little bit of performance. But then I thought, okay, but this is actually a very powerful thing in if we want to look at language learning, because we can. We also are trying to do these two things, right? We're trying to do comprehension and production, and but we have a clearer idea of what the objects are that we start with in the first place. So maybe we can get it to work. So yeah, in our case, we did get it to work, at least to some extent, as you will see in a little bit. Okay, one more detail is that the non-linearity that we use is sigmoid, which will become important in a little bit. Okay, so this was for the learning part. Does it make sense to everyone how to? Oh wait, I should probably say we just calculate cross entropy between the output distribution and the one-hot encoding of the first input word, right? So that's the way in which this is trained at the end. Does this make sense? Do people understand how the self-supervised learning works? So sometimes, let me just say that sometimes I get the question, what if the comprehension module outputted the sun here, right? And then the production module inputs the sun here, and then the output is duck again. There will not be a mismatch here, right? If as long as their mismatch is the same, right? As long as they make the same mistake in a way, right? then there won't be no update to the model. And that's true. But the thing about cross-situational learning is this will never be the case over many occurrences, right? Because there will not always be a sun that you can map the duck to, right? This can only happen if the two objects always appear together. So that's, in the end, that's what's really providing the signal, is still the co-occurrence of objects and words over many instances. Okay. Okay, so and then I said we could do something else with the two models, with the two modules, which is selecting input actively, selecting input that would be helpful to our learning. And in this way, in this case, we use the modules in sort of a flipped way, right? So what we want to do now is, and in an analogy to human learning, what we are trying to mimic is a parent following their child's attention. So this is something that we know parents do. Very often they will talk about objects that are already in the field of vision, already the focus of the child's attention, and this will be what they will be talking to their child about. So this is sort of the idea. So what we're doing is, for every object in the scene, we want to know whether it would be helpful to receive input for that, right? And the idea is that since children are curious, they might use these same kind of considerations to direct their attention to objects that then the environment provides input for, right? And they might do that in sort of a strategic way, right? They might do so in a way that would optimize their learning. So what do we do for every object in the scene? We feed it to the production module, which outputs a label, right? Then again, we do the comprehension task with this label that the production module provided, and paired with all the objects in the scene, and then we output an object again, right? Which is the most likely, or this distribution over the softmax over the objects in the scene, basically. And again, what we can do is we can compare the two, right? So we can compare whether this object is the one that we were actually looking at. Why is this helpful? Well, if the two do not match, then somewhere in our language knowledge, something is wrong, right? Because either the mapping of the object to the label is wrong in the production module, or the mapping from the label to the object in the comprehension module is wrong, but somewhere along the line we made a mistake, right? And then if we do, that might be a good object to receive input for. That's the basic idea. That's the basic idea, but the real idea is a little bit more complicated. So this is again based on the Toomey and Westerman paper that I referred to before. So in reality, they consider sort of two factors. So one of them is, are you indeed wrong, right? So what's the difference between the input and the output of the production module and the comprehension module, right? So this is basically do the objects match, or do they mismatch? Plasticity is something else. So what plasticity does at an intuitive level is that it is highest for items for which the learner is unsure. Basically, what we do is we look at the derivative of the output distribution. So all of these are sigmoids. This formula right here, this O1 minus O, right, is the derivative of the softmax function, which is summed over all the items in the output distribution. And this is highest when the sigmoid is like in the middle, right? So that means two things. So it means that the learner is unsure. It also means that an update to the model will yield a very big change in your output state if you would see the same example again, right? Because this is also what is training the model actually, right? Is the gradient here. Okay, so that is why plasticity. So both these things do something quite different, right? So the first thing says, okay, I want to look at items that I am wrong about, and the other is, okay, let me just, I would like to look at items that I think I don't really have a very strong knowledge about, right? That's what you're selecting for here. And then in the definition of curiosity that Toomey and Westerman use, you combine the two. So this is basically just the product of the two. but summed over all of the objects. Okay, so these are different definitions. So what we did is we trained 20 models in each of these conditions. So for all of the models, they receive all of the images in our data set once. And then we just select one of the objects. And the selection of the objects is either according to one of these metrics, or it is at random, which means that in every epoch, they might see a different object, right? Well, that might be the case anyway, but that's also the case for the random one. So it's not that we select the same object every time for these images. And then we do 20 runs in each of the conditions. Okay, how do we evaluate if our model learned anything? Well, basically we just use the accuracy on the comprehension task and the production task. So how good is the model at mapping words to the correct object, and how good is it at doing the other task, right? Naming objects, basically. So here are the accuracies and standard definitions over 20 runs for all of the conditions. The first column shows the comprehension accuracy. And what you can see is that the curiosity condition definitely outperforms all of the others, right? But the follow-up is actually the random condition. Both selecting items according to plasticity and according to subjective novelty are worse, particularly regarding subjective novelty, right? That one is really not doing very well. In addition, the standard deviation for curiosity is lowest, which means that all of the 20 runs end up more or less around the same level, right? Whereas for the other ones, except for subjective novelty, but that one is not really working anyway, right? The spread is a bit bigger than it is for the models trained in a curious condition. For prediction, we see more or less the same pattern. The numbers are much lower here, right? So the accuracy is really not very high, right? But keep in mind that the way that we constructed this task, what the production module does is an output distribution over more or less somewhere around 4,000 words in the vocabulary, some of which are very infrequent. So yeah, that's maybe not the best framing of the task. I will also go into that a little bit later. So that these numbers are low is not, I'm not very concerned by. They are definitely all above the baseline, which is the important thing here, I think. So this baseline here is the frequency of the majority word, and all of them perform better than that. So at least they've done more than just pick out the majority word, right? Okay, so I wanted to give a little bit of a closer look about at the performance of these models. So first of all, the orange lines are the curious models. As you can see, they are the ones that are sort of closest together, right? Out of all of these models. So I actually don't know how well this translates to your screen, because these are very tiny graphs. So right here we see this sort of orange band. This is the accuracy after each epoch of training on the training data on this side of the graph. And on this side we have the test data. So comparison on the test data, well, maybe there's like slightly lower performance on the test data, but like both of them are kind of like similar, right? All of the models end up sort of around the same level. And when we look at the random condition, this is not the case. So some of these end up sort of similar to the curious condition. So blue is the random condition. Here as well, right? So some of them do end up at the same sort of level as the curious ones do, but the spread is much larger, right? This is the lowest one in the blue condition here, and this is the highest. Same here. For plasticity, I have to say plasticity to me is the most difficult to interpret, and it's the one that I'm most curious about exploring further. But the general images, they kind of like they also have this initial benefit that the curious ones also have, right? So the random condition, not only do they end up like a little bit more spread out, but also the ones that end up higher as performing as well as the curious conditions take a lot longer to get there, right? So curiosity really helps to get up to speed fast, right? The orange ones shoot up. Actually, after one epoch of training, they are already outperforming all of the other ones, right? So even if they catch up eventually, it goes much faster if you select according to curiosity. For plasticity, this initial benefit seems to be there. It doesn't quite start at epoch 1, but it's definitely from epoch 2. It's outperforming sort of the random models, but then they kind of like plateau, and they don't really. So some of them end up comparatively, but some of them stay a little bit not very great, and they don't really perform very well, and they don't really get to a higher level at some point anymore. So there's something going on there that I'm not entirely sure how to interpret that yet, but yeah, we can get into that if you want. Now for this curious case of subjective novelty. So we have these guys, right? Boom, I know everything about this data. That's basically what they do, right? And then you have these guys that kind of like stay around baseline on the or about the training data, right? And then none of them have learned anything that is generalizable to the test data, right? There is none that outperforms the baseline, basically, right? This baseline is actually incorrect. I think. Let me see. Yeah, the baseline should be around 0.9. No. This is the comprehension. Okay, no. Right. So that's true. Yes, what I said was true. Yes, that's also true. Right. The accuracy is 0.28, and it is also that's also the baseline. Yes. So none of them learn anything generalizable. Now this part, I think I was very surprised by when I first saw it, and then I thought, but this is very obviously, this makes a lot of sense, because what does subjective novelty do? It basically selects for things that your language knowledge is not a good predictor for, right? So it selects for outliers. It selects for things that do not fit the general picture, right? It selects for idiosyncrasies, basically. So what you're learning is you're learning the weird stuff about your data. So eventually you will remember the test data, but you will not have selected to learn about things that you can generalize about, right? That's what is going on there with subjective novelty. Should we go into yeah, we can go into the production data, but it's kind of like a similar story. So I don't think it makes a lot of sense to go into that. Yeah. I think this is more interesting. So this is, how are we for time, by the way?
Doing well.
Yeah,
we're at 10:40. Yeah.
Okay. So this is kind of like the last thing that I wanted to show in terms of results. So when we saw these results, we kind of, the thing that you really want to do now that you see how these different, so the thing that's kind of confusing about this is that even though subjective novelty and plasticity by themselves are not helpful, combining the two and just taking the product is helpful for selecting helpful input, right? We know, because we saw that this really improves performance. It both helps to learn faster, and it helps models converge to this level more robustly. But what's going on? Because its constituents don't really do this, right? So what we wanted to do is we wanted to look at what are the objects that these metrics actually select. So when do they select the same thing, right? What's clear is that in the first epoch of training, so at 0, right, there is no language knowledge yet, or there is during this epoch, but not at the start. Overlap is almost complete between curiosity and subjective novelty. So right now, subjective novelty is driving the choice of objects by curiosity, right? This component of the product is actually what determines it. It's probably the largest component at this point. So this is determining which objects are being chosen. And this kind of makes sense, right? We don't know anything yet. Let's first correct all the things that our random initialization makes us wrong, make the wrong predictions, right? That's what's going on. And then after this epoch, actually, this really sort of goes down, and actually the overlap of curiosity and plasticity, which is the blue line here, shoots up, right? So after this, curiosity and plasticity start to overlap more and more and more. This overlap continues to grow. And then there are some cases in which the three overlap, and there are also some cases in which curiosity and subjective novelty overlap. I should say that we have these three metrics, but actually in quite a significant portion of our data, we only have two objects, which means it's a bit more difficult to interpret, because it means that not always are there objects A, B, and C to choose from. Sometimes there's just A and B. So you don't really know like what the overlap in choices means there in those cases. But yeah, so it's a caveat there. But okay, so I think we're getting some insight into what is going on now, right? So at the start of learning, it's helpful to look at stuff that your assumptions based on nothing, right? Based on random initialization. It's useful to kind of look at those examples, but after that, it's more helpful to look at items that you're not so sure about, apparently, right? That's what this indicates. Now, this also leaves some questions, right? Because we've also seen that plasticity doesn't actually perform so well. So some of them do end up there, up with the performance of the models in the curious condition, but they're not guaranteed to end up there. I'm not entirely sure what's going on there. My hunch is that models that select input according to plasticity are more likely to end up in sort of local minima, because you never have, so there is an incentive in curiosity to correct things that you're wrong about, right? And there is none of that in plasticity. So that would be my guess, but this is really a guess. I have no data to back this up. So that's something that I want to look at in future as well. Okay, so concluding, we found that this curiosity indeed leads to higher accuracy and more robust convergence, and also faster learning. That's actually, I think, from a cognitive perspective, that's maybe the most important finding, right? Because one of the things that cognitive scientists always say is, yeah, these neural networks, we want to do like experiments on them, but the fact that they need these amounts of data is very cognitively implausible. So the fact that this speeds up learning from a cognitive perspective is very important. Right, but we know that these individual components by themselves do not, at least not in our test set. So these are the main findings. What are the things that I want to work on next? I think maybe might be interesting, and I will not get to all of them. So maybe if there are people who are interested in working on this too, then please reach out to me. So one of the things is that I'm not very happy with the definition of this task, of this production task, as just being a distribution over the vocabulary, because it means that these words at that point are just like symbols with no real semantic representation, right? So at the start, I start with word appendix, but at the production module, I don't have them. So I've been thinking about ways to do that with outputting a vector that is of the size of word embedding, right? And then just calculating like the distance to the word embedding that I started with in the first place. I'm not sure that this is going to work technically. I'm not entirely convinced yet that it's going to work. It seems like you're more prone to getting to this, so the learning signal will not be as strong for selecting the correct object, which is kind of driving this learning mechanism. So you do have distance there, but yeah, I don't know. Well, I'm trying to figure out if this is going to work or not. That's the bottom line there. I would like to work with multi-word expressions. I would actually like to work with full sentences that might be naming multiple objects. This is something that I'm implementing right now and trying to do. So not just look at one object at a time, but basically, consider all of the words in the sentence. And I really want to get this model into some simulations of dialogue setups, or at least some kind of, so the idea, so since we have a comprehension module and a production module, it would be very fun if our model could sometimes learn by putting some language out there and receiving feedback in some form, not feedback in the sense that they are wrong or they are correct, but because they have a dialogue partner that is willing to communicate with them and is already a net language learner. So that is also something that I definitely want to do, and I have some initial ideas for, but I haven't really worked out yet. So yeah, that's another thing. Okay, that was what I had prepared. Thank you all for your attention. I hope it was interesting, and if you have any questions, I would be very happy to discuss with you.